Hello, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This video is for grade 10 students who are studying quadratic relations. In this video, we'll focus on working with the vertex form of a quadratic relation. Just a reminder that this is what the vertex form of a quadratic relation looks like. And we like to work with these because if it's in this form, you can instantly tell what the vertex is by looking at h and k. And of course, A will always tell you, regardless of what form you're in, A is consistent. A will tell you the shape of the parabola. If A is greater than 0, it opens up and has a minimum. If A is less than 0, it opens down and has a maximum. And the value of A tells you if it is a stretched or a compressed shaped parabola. So here's the question that we're going to be answering in this video. If you haven't already seen this question and attempted it, I recommend you pause the video here, try it on your own, and then replay from this point when you're ready to check your answers with mine. Okay, let's get into it. It says, Jill is on the top of a building and throws a ball in the air. The height of the ball, h, so the height of the ball above the ground is given by this equation. And h is height and t is time in seconds. So before I look at these, I just want to get a quick idea about what's happening. We have actually let me just do this. So this person, Jill is on a building, and I probably drew it a little too tall there. So Jill's on the top of a building and she throws the ball, and it probably does something like that. So we expect to see this sort of behavior where there's a ground down here and there's the height of the building and so on. So that's what's happening. So again, this is the equation and there's all these questions we have to answer. So let's just jump right into it. So first of all, what is the height of the building? So again, if you think about this diagram, how can we find the height of the building if this is about the height of the ball? Well, when the ball was thrown, it was thrown by Jill from the top of the building. So the height of the ball is going to match the height of the building the moment she throws the ball. In other words, when t equals 0, at the very start of the ball's behavior or the ball's motion is when it's at the top of the building. So when t equals 0, the ball is at the building height. So asking for the height of the building is the same as saying the height of the ball at the start. Meaning the start of when the ball's motion takes place. And of course that means when this equation actually starts to come into effect. So that means we need to let t equals 0 and find h. So that's an algebra question. If we sub t equals 0 into this equation, what happens? So t is now 0, everything else of course exactly as I see it. And then I just have to do good algebra order of operations to solve. So first, inside the bracket, 0 subtract 3 is -3. And then there's an exponent to deal with. -3 squared is 9. And then multiplication, -5 times 9 is -45. And then finally the addition or subtraction, -45 plus 180 is 135. So when t equals 0, the height of the ball is 135 meters, and therefore the building is also that high. And there might be a little give or take there, but that's the best we can do with the information. Okay, next question. What is the maximum height reached? Well, anytime you're dealing with a quadratic relation and a word maximum or perhaps minimum comes up, you know that the question is thinking hey, look at the vertex and interpret it properly. So let's find the vertex, and because it's in vertex form, this is really easy to do. The vertex is h comma k, remembering that h is actually the negative of what you see, because 3, if subbed in here, makes the bracket 0. So 3 comma 180 is the vertex. And in the vertex, normally it's xy. In this case, it's th. So the height is right here. So therefore, the maximum height of the ball is 180 meters off the ground. Easy to do if you have the vertex. How long does it take for the ball to reach maximum height? So again, we have this word maximum, which means we know that this is a question related to vertex. So again, vertex is at 180. And because it's not xy, it's time and height, there's the time it takes to reach that maximum height. So how long does it take for the ball to reach maximum height? We can say, therefore, it takes 3 seconds to get to maximum. Okay. So obviously those two questions are related, and usually, you know, if you know one, you know the other. Just keep track of which one's the x and which one's the y. In this case, the time and the height. Next. How long after throwing it does Jill see the ball directly in front of her on its way back down? Okay, so let's rethink kind of the visual, because I like the visual. So don't forget, here's Jill standing on top of the building, and she threw the ball, and it did this sort of thing. So she's originally at the same height as the ball, and the question is asking, when does she see the ball on its way back down? So what time is it when the ball is coming back down to see her? So we could substitute in the height of the building, which we calculated in part A, but there's actually a quicker way that demonstrates a bit more understanding. We know that every parabola is symmetric through a vertical line at the vertex. In this case, the vertex again is at x equals 3. So what that means is that from time 0, when Jill throws the ball, it takes 3 seconds for the ball to go up to the vertex. And because of the symmetry of a quadratic, it must also therefore take 3 seconds to come back down to the same height that it started up. So if it took 3 seconds to go up, and then 3 seconds to go down back to the original height, then it must have taken 6 seconds for the ball to be thrown up and come back down to where Jill can see it directly again. So the answer is 6 seconds, and we found that through symmetry. There's a longer way to do it, and again, the longer way would be to know that Jill's height is the same as the height of the building, and from part A, we found that that was 135 meters. So we could sub that in and then solve for t. So let's just do that to, you know, show that we're doing it. So if I sub 135 here, I'm going to solve for t. So subtract 180. 135 minus 180 is negative 45. Divide both sides by negative 5, that's 9. Take the square root of both sides. So the square root of 9 is 3, or negative 3. And when I take the square root of this side, it just loses the squared, so I don't need the bracket anymore. So if I add 3 here, I get 6. And if I add 3 here, I get 0. And again, that's excellent, because that means that at Jill's height of 135 meters, again, that's the height of the building too, the ball is at that height at t equals 0 when it starts, and at t equals 6 when it has gone through the vertex and then passed down through this symmetry. Okay? So again, there was a really quick way to get that answer if you really understand symmetry, but you can also calculate it if you need to. Next, how far above the ground is the ball after 5 seconds? So this statement is telling me that t equals 5, and I need to find what the height would be. So this is just pure algebra. I'm going to sub t equal 5 into the equation, and then just do good algebra, order of operations, and find the height. So inside the bracket, 5 subtract 3 is 2. Exponent on 2, 2 squared is 4. Multiplying, -5 times 4 is -20. And then finally, addition and subtraction. -20 plus 180 is positive 160. So after 5 seconds, the height of the ball is 160 meters. Okay. And it's nice when things make sense. Again, if we go back to this question, we know that 6 seconds it had gone up and come back down to 135 meters. So after 5 seconds, we would expect it to be, I don't know, here, which needs to be somewhere between the maximum height and that original height. And we found that it was 160, which is really nicely somewhere in between here. So after 5 seconds, that's the height of the ball. Next, Mr. Clark works on the 10th floor. I just realized I skipped question E. So give me 1 second. I'm going to come back and do question E. Yeah, I could edit the video, but I'm not going to. E is, how long is the ball in the air? Okay, I'm just going to write it. Can't be bothered to edit the video. You like this stuff, right? Just me blathering on? Sure. Okay, so how long is the ball in the air? So, how long is asking a question about time? So the rest of this must be giving me information about the height, because in the equation, I need to know either time or height to find the other one. So let me just grab the equation. The sound effect was not real. That was just me pretending to be a sound effect person. What happened? Okay, that's better. All right, so there's the equation. So again, since I need to solve for t, I must be able to substitute something in for h. So how long is the ball in the air? So remember the situation? Let me go back to a diagram. There's a good diagram. And I'll go back to the earlier one. Here's the first diagram we made. So how long is it in the air? In other words, what time does it take the ball to travel from this original spot with Jill all the way up to the vertex and then all the way down to the ground? So I'm really asking, what is the time that the ball gets to this point? Well, what is the height at this point? Well, that's when the ball's on the ground, so the height is 0 when the ball is done traveling because it's hit the ground. So what I need to do in this question E is I need to let h equals 0 and then find t. So, and that's because, again, the ball is in the air for the whole time it's traveling, but once it hits the ground at h equals 0, it's done moving. So let's substitute 0 in for h, and then we will solve for t. So once I sub 0 in for h, now I'm trying to solve for t, so I have to remove math but in order to isolate t, and we start from the outside or work our way in. I'm going to subtract 180 from both sides. Divide both sides by -5. Take the square root of both sides. So when I take the square root of 36, I get both 6 and -6. When I take the square root of this, it just cancels out that squared, or that exponent too. So the square root of 36 is 6, or -6. And then I have two little equations, add 3. add 3. So one of the answers is sort of weird. How can time be 3 seconds in the past? So the reason for that is if we think about the graph of this, again, we know that this is roughly what this parabola looks like. So when it gives me this -3, it's telling me sort of the part of the graph that doesn't exist in this reality. But again, the math doesn't know that this is a time and height problem. It's just doing the math for me. So one of my answers was 9, and that makes sense, 9 seconds to get here. The other answer of -3 is what we call inadmissible, because although it is algebraically accurate as an answer, it's not admissible to the actual problem about a ball's time and height. So my answer is 9 seconds of air time for the ball. Okay, so that was E. So I already did F because I did it out of order, so now we're on G. Mr. Clark works on the 10th floor, which is 30 meters above the ground. How long after it is tossed in the air will Mr. Clark see the ball pass in front of him? So obviously this is a height reference, and how long is saying find time. So I know the height is 30. I want to know what time that occurs at. So again, I'm going to substitute in the height that I know, and then algebraically solve to find what the time would be. So there's my equation with the height I know. And now I'm going to solve or isolate t. Again, I'm going to subtract 180 from both sides. Divide both sides by -5. It's just a coincidence that I got 30 again. Take the square root of both sides, square root of 30, I'll get a decimal. Square root of this just canceled out the squared. So what is the square root of 30? And I'll just round to 1 decimal. It's about 5.5. And it's also -5.5. So add 3 here. Add 3 here. And again, one of them doesn't make sense. It doesn't make sense to talk about negative time, so that's inadmissible. So my answer would be 8.5 seconds. So therefore, at 8.5 seconds, Mr. Clark can see the ball because it passes by his window. And let's just make sure that that makes sense. So if we go back to this diagram, 30 meters. So again, the building itself was 135. 30 meters would be like, say, here. So that's a bit before 9 seconds, which 8.5 is. So everything makes sense. And then finally, we've been sort of doing this the whole time anyway, draw a sketch indicating all height and time information. So I'm going to use just the tools I have to make at least some of this nice and neat. So I'm going to use these lovely straight line tools. And then what do I know? So the important information, so if we sort of sketch it out, I know it looks like this. So what do we know? Well, this must be at 135 because that's where it started. And the maximum here, that would be at 180 because if you remember, we found that the maximum was at 180 and it took 3 seconds. We know that this is at 9 seconds and 6 seconds would be about here, right? Because that's when Jill sees it come back down because she's still standing on the building. What else was important? Oh, Mr. Clark. Mr. Clark, who is 30 meters off the ground, sees the ball at 8.5 seconds, so that makes sense. And then there was when t equals 5. So when t equals 5, the height of the ball, right about here, which we calculated to be about 160. So everything makes sense. Yay! I like when math makes sense. So this is time, and this is height. And again, this is a sketch, not a graph, right? a graph, I would do things like put it on a grid, and I would label more consistently, and like, because normally this is not acceptable to go up 30 units and then up 105 and then up 25. So, you know, this is just a sketch. And really the whole point of the sketch is to make sure that all of the values we found make sense with this question. So I hope that helps. And I just want to remind you that thank you for watching my video, but that's not studying. When you study math, you're actually doing math. So go and find more questions. I've left you some. There's lots in your textbook. And practice this math. Thanks for watching.